This project examines whether a tabular class scikit-learn model can function as a screening layer for stroke risk on a publicly available Kaggle dataset. The file in question comes from the user Ranagulam Nabi and contains 110 patient records, 11 predictors after the record identifier is dropped, and a single binary outcome indicating a prior stroke. 4.87% of those records are positive. The central question is not whether a model can achieve high accuracy. At this prevalence, predicting negative on every row reaches roughly 95% accuracy and identifies no positives at all. The question is whether a simple, interpretable model can flag the records a clinician should review next. Framing this as screening rather than diagnosis shapes every decision that follows, from the choice of primary metric to the placement of the decision threshold. I present the dataset, the pre-processing pipeline, 2 candidate classifiers, the evidence for preferring one over the other, the governance scaffolding that would be required before any deployment, and the limitations that keep this work firmly in the educational category. The screening framing is not rhetorical. It is the load-bearing decision that determines which errors are acceptable. Diagnosis requires a clinical setting, a licensed professional, and information well beyond any tabular dataset. Screening asks a narrower question. Given these 11 predictors, which records warrant additional human review? A model that answers that question well does not need to be correct about every positive on its own. It needs to rank positives near the top of its probability distribution so that a finite review budget catches most of them. That framing has 2 consequences for evaluation. First, the cost of a missed positive is larger than the cost of a false alarm, because the missed positive leaves a patient at risk unexamined, while the false alarm merely occupies reviewer time. Second, accuracy is disqualified as the primary metric before any model is fit. The baseline classifier that predicts negative on every row reaches 0.951 accuracy, 0 precision, 0 recall, and 0.5 ROC-AUC. That number is a ceiling on how misleading accuracy can be at 4.87% prevalence. The dataset contains 110 rows and 11 predictors after the identifier column is removed. Age, average glucose level in milligrams per deciliter, and body mass index are continuous. Hypertension, heart disease, ever married status, gender, and residence type are binary. Smoking status and work type are categorical with 4 and 5 levels respectively. The outcome is a single binary indicator of prior stroke. 249 records are positive and 861 are negative, fixing the prevalence at 4.87%. Body mass index has 201 missing values, roughly 3.9% of rows. Every other predictor is complete. I imputed the missing BMI values with the training set median and applied that same. The 80/20 stratified split produced a test set of 122 rows with 50 positive cases and a 4.89% positive rate, closely matching the source distribution. One-hot encoding expanded the categoricals, and standard scaling was applied to the continuous features for the Logistic model only. The tree ensemble requires no such scaling. 2 classifiers were fit on the same pipeline. A logistic regression with L2 regularize a chain at C equal to 1, and a random forest with 100 trees, bootstrap sampling and random feature subsets at each split. Both use the scikit-learn setting class weight equal to balanced, which re-weights the loss function so that each positive example carries roughly 20 times the gradient contribution of each negative example. That single parameter is the most consequential choice in the project. Without it, the random forest collapses onto the majority class and recall approaches 0. Recall on the positive class is the primary metric because a missed stroke positive record is the error that matters most in a screening context. Accuracy was tracked for completeness and for contrast with the 0.9511 majority baseline. Precision ROC-AUC and Precision Recall-AUC and Precision Recall-AUC were computed to describe the threshold surface. The test split was held out for the entire fitting process. No cross-validation was performed, which I return to in the limitations. The exploratory work shows where usable signal lies before any model is fit. Age separates the classes most clearly. The positive class distribution is compressed into older decades, effectively absent below 40 and rising steeply through the 60s and 70s. Average glucose level shifts rightward for positive cases, with a higher median and a longer upper tail, consistent with the clinical association between dysglycation between dysglycemia and cerebrovascular risk, reported in Interstroke, O'Donnell et al., 2016. BMI separates the classes weakly, and some of the apparent separation is an artifact of median imputation, compressing variance among the 201 records that were missing. The binary predictors tell a complementary story. Hypertension and heart disease prevalence are several-fold higher in the positive class than in the negative class, matching the literature on vascular risk factors. Fagan et al., 2015. Varani et al., 2015. Varani et al., 2021. The correlation heat map confirms that age, hypertension, heart disease, and glucose. None of these associations are causal claims. They describe patterns in this file. The logistic regression results on the held-out test set are the baseline against which the tree ensemble is judged. Recall on the positive class is 0.8, meaning the model correctly flags 40 of the 50 positive cases in the test split. ROC-AUC is 0.8437, and Precision Recall-AUC is 0.26. 83 above the precision at the 0.8. Recall operating point is 0.1481, which translates to roughly 6 to 7 flagged records per confirmed positive. Accuracy drops to 0.7456 at this operating point, which is well below the 0.95 majority baseline, and illustrates exactly why accuracy is the wrong metric here. The model trades accuracy for sensitivity. The default 0.5 threshold is conservative at this prevalence and produces lower recall. The 0.8 recall operating point reflects a deliberate choice of threshold rather than a model hyperparameter, a distinction I develop further on the recommendation slide. The random forest result is the clearest argument in the project. Recall on the positive class is 0.16, meaning the ensemble catches 8 of the 50 test positives and misses 42. ROC-AUC is 0.8124, and Precision Recall-AUC, both below the logistic model. Precision reaches 0.2963, and accuracy reaches 0.9403, numbers that look attractive in isolation, but describe a model that has defaulted toward the majority class. Doubling precision while collapsing recall is exactly the wrong trade for screening. The confusion matrix shows most positive cases landing in the false negative cell, which the mechanism is structural. Each bootstrap sample contains only a handful of positives at 4.87% prevalence. Each tree learns a conservative decision surface, and the majority vote across 100 trees compounds that conservatism. Class weighting helps the logistic loss directly but operates less effectively on the tree splitting criterion. Feature importance places age at 0.467, average glucose at 0.1589, and BMI at 0.1569, together accounting for 71.3% of attributed importance. I treat this project as an educational demonstration rather than a clinical tool, and the limitations justify that stance. The data is observational, so every association the model describes is correlational. No causal claim can be made from 110 Kaggle rows. Provenance is opaque. The file's population, collection dates, and coding conventions are not documented to the standard a health application would demand. Body mass index imputation compresses variance on 3.9% of rows and may dampen signal from patients whose BMI was most informative. Critical predictors are absent, including blood pressure, lipid panels, family history, and medication records. Any of these would likely improve discrimination. The evaluation used a single 80 or 20 split, rather than cross-validated folds, leading point estimates without formal uncertainty intervals. I did not run a subgroup fairness analysis because the cells become too thin at 50 positives to produce stable estimates. Deployment would require prospective validation on an independent cohort, stratified monitoring across age, sex, smoking, and hypertension subgroups, and a documented threshold review cadence tied to cost asymmetry. The recommendation is to operate the logistic regression model at a recall first threshold, with the 0.8 recall point offered as a default subject to stakeholder review. The threshold is not a model hyperparameter. It is a design choice that fixes which error the organization is willing to accept more of. At 0.8 recall, precision is 0.1481, and reviewers see roughly 6 flagged records per confirmed positive, manageable for a primary care intake workflow with clinician review attached. Logistic regression wins on the metric that matters, on interpretability, and on calibration quality. The coefficients are auditable, and the probability estimates are close to well-calibrated, which makes the threshold conversation with stakeholders coherent. The implementation places the model at intake scoring, routes flagged records to clinician review, and treats every score as a starting point rather than a conclusion. Governance obligations include independent patient validation, stratified monitoring across the subgroups named earlier, a documented threshold review cadence, and a rollback procedure for distributional drift. Future work includes SMOTE, Jola et al., 2002, K-fold cross-validation, permutation importance, and cost-sensitive learning, tied to an explicit cost matrix. The recommendation stands on 3 findings drawn from the evidence already presented. A 4.87% positive rate makes accuracy misleading, and the majority baseline reaches 0.9511 without clinical value. Class-balanced logistic regression reaches 0.8, recall, and 0.8437. ROC-AUC. On the test set of 22 rows, the random forest collapses to 0.16 recall, despite a higher 0.2963 precision and a higher 0. The threshold is a design choice rather than a hyperparameter, and the 0.8 recall operating point is offered as a defensible default for a primary care screening workflow with clinician review attached. The repository contains the preprocessing pipeline, the fitted models, the test set predictions, the figures shown in this deck, and the reference list. Ranagulam Nabi, N.D., Feigen et al., 2015, O'Donnell et al., 2016, He and Garcia, 2009, Forla et al., 2009, Cholala et al. I welcome questions on the threshold trade-off, the class imbalance handling, the subgroup analysis I did not run, and the governance scaffolding that would be required before any clinical use of a model like this.